السلام عليكم. مساء الخير مهندس رشا.
مساء النور، أهلا دكتور.
سلام دكتور أحمد.
السلام عليكم، يعطيكم العافية جميعا.
أهلا دكتور أحمد، مساء الخير.
أهلا دكتور أكرم، الله يعطيك العافية.
الله يعافيكم.
مساء الخير جميعا، يعطيكم العافية. معكم مهندس سارة تويسي من الجامعة الأردنية. شكرا لحضوركم ورشة الإيكوكار لليوم. ورشتنا لليوم راح تقدمها الجامعة الألمانية أوستفالين ليفه and راح تبدأ ورشتنا الآن الساعة 4 إلى 6:30. راح ننتظر يعني دقيقتين يكتمل شوي العدد، وراح نبدأ في الويلكمينج سبيتش by بروفيسور أحمد السلامة, the General Project Coordinator at the University of Jordan. So we will wait 2 minutes until we have like a completed the number of attendees, and we will start with the welcoming speech by Professor Ahmed Al-Salame.
تمام.
السلام عليكم دكتور أحمد. السلام عليكم جميعا.
عليكم السلام. أنا دكتور سلمان.
تحياتي.
هلا دكتور سلمان، كيف حالك؟
هلو everybody. هلو. السلام عليكم.
هلو دكتور سلمان، مساء الخير.
هلو، يا أهلا وسهلا.
حياك الله.
So let me give a brief like of the agenda of our workshop for today. So we'll start with the welcoming speech by Professor Ahmed, the General Project Coordinator at the University of Jordan. And we will have another presentation of hydrogen vehicles, state of art and perspectives by Professor Salman Ajib. And then we will have another presentation by Dr. Sabine regarding charge transport transport in batteries. This will be for 1 hour, and then we will have 15 minutes discussion and questions for the speakers. So let me now give the mic for Professor Ahmed Al-Salaime, the project coordinator of our project, EcoCar project. Professor Ahmed, the mic is yours.
شكرا سارة, يعطيكم العافية جميعا. Good evening or good afternoon. It is our pleasure to be with you today, and would like to thank all our partners in EcoCar projects. Also special thanks to Professor Ajib and his team from Ostwestfalen-Lippe University in Höxter in Germany. Maybe to give you, before we start with this like monthly workshop, that as you know that we have like within EcoCar projects 2 hours workshops every month. This workshop is like a part of capacity building plan that we have in the field of electric and hybrid car. And maybe to give you a brief, if you make slideshow, Sarah, give you a brief about like EcoCar projects maybe within a few minutes. This is like an Erasmus Plus projects supported by European Commissions. It is 3 years. We are still in the first year, and we aim to establish like a diploma in 8 Jordanian universities in the field of electric and hybrid car. So this project, I think that is very important for Jordan. As you know that the whole world is now converting to the clean energy, to the renewable energy. And as you know that according to the energy strategy in Jordan, within 2030, I think that we will have almost 30% or 31% of our energy or electricity needs from renewable energy, according to the recent like strategy that which was announced by His Excellency the Minister of Energy. This ratio will be also increased to 50%, which means that I think that using electric cars will be like obligatory in Jordan and in the regions. From the University of Jordan, in these projects, we have like a big team from like different departments at the School of Engineering, from mechanical engineering departments, from electrical and from mechatronics, in addition to the like center of consultations. Next, Sarah. Yeah, and this is what we mentioned about the main objective of the projects, and we will start the implementation process next September. So next September we'll have like 3 types of diploma. We'll have vocational diploma, which will be introduced by the Center of Studies and Consultations, and we'll have also a professional diploma. This will be like at the level of the master degree in the field of engineering, which will be given by the University of Jordan and other Jordanian universities. In addition, we'll have like 2 years community or the college diploma. This is also a third part of the diploma. Also, we'll establish like different labs and different EcoCar centers at 8 Jordanian universities. In addition to integrate some also courses related to the electric and hybrid cars in the curriculum, especially in the bachelor and master. We'll also establish or create a platform. In this platform, we'll have like a list of the courses, and it will be open for also all universities, not only for the partner universities. And we are concentrating on like strengthen the cooperations between university and stakeholders. So therefore we have a network that contains members from different stakeholders in Jordan and in Europe. And as we said that some indicators about the projects that like establishing the diploma and also conducting continuous workshops, and in addition to we have continuous also evaluations and quality assurance tools to achieve the projects and to harmonize the courses and the teaching methodologies between Jordanian universities and European universities. Next slide. Yeah, and as we said that we'll have like 8 centers, 8 labs. These labs, hopefully that within a few months, they will be ready in 8 Jordanian universities that who are members in the projects. These universities are University of Jordan, Jordan University of Science and Technology, Mu'ta University, Tafila Technical University, in addition to Al-Balqa Applied Universities, and we have a university, and we have 3 private universities, which are Applied Science Private University, Al-Zaytuna University, in addition to Al-Hussein Technical University. So we'll have 8 labs, we'll have like 8 diploma, and as I mentioned that we have 3 different of these diploma. In addition, we'll have like many training workshops that next year we'll have these workshops in Europe and also in Jordan, and we'll also host our European partners who are experts in this field to give these workshops in Jordan, and you will also receive invitations when we'll have these workshops, in addition to launching the platform which I mentioned. Next slide. Yeah, as we said that this is what we'll concentrate on in the projects, to have like qualified engineers, technicians, and also to increase the level of provided service, since as we said that many car companies announced that in 2030 all their factories will convert it to produce only electric cars, which means that the electric cars will be dominant in the national, regional, and international markets. So this electric car, as I mentioned, that it is like environment friendly, and it will help to reduce CO2 emissions and to reduce global warming. Yeah, since 2-3 weeks that the COP, this is in Glasgow, was also finished, and they announced that now they want to have like only 1.5 degree temperatures increase in the atmosphere, and which means that it would be more dependent on like environment friendly measures. Next, Sarah. Yeah, so we have like different work packages related to the preparation, development, quality plan, disseminations, and management. Yeah, as you said that before we designed the curriculum, we did also a study and we have also these connections between stakeholders and the enterprises, and any colleagues from any enterprise can join our network to be a member with us, and we will have also some activities and workshops for the networking members. Next. Yeah, also before we design, as I said, that the curriculum, we did also a study in the market and with the stakeholders, with the students, with the faculty members, and we extracted a report about the market needs, and therefore the curriculum was designed according to this market need. Next. Yeah, also, as I mentioned, that this workshop is within the capacity building plan, and we'll have many workshops in our European partners. So this is an example about the workshop which was conducted by our partners in Aachen University. Aachen University is expert in energy storage, in addition to our partner in Univac, Italy, about also they conducted a workshop about internal combustion engines. Also, it was another workshop with our partners from Greece, NTUA, about also vehicle dynamics fundamental. We have also a 4th workshops with Budapest University, also about internal combustion engines in hybrid systems. And this, I think that workshops. Also, we have 5th workshops also by University of Deusto in Spain about also vibration acoustic comfort in vehicles. And the 6th workshop that we have today with Ostwestfalen-Lippe University in Höxter. So we'll hear today from Professor Ajib and his colleague about this workshop. Yeah, as I mentioned about the establishing of the labs. Now we have the tender, and soon that we'll have the equipment in different Jordan universities. So our students, our trainees will be also qualified in this field. This is like some labs at the Applied Science University, and this is example about our visits to the car companies in Jordan to check with them the competencies that they need from the students. Next. And about the courses, we started now developing the curriculum, and this is the most important work package that we have. And within 3 months, all courses and modules will be ready in English, and then we will translate them to Arabic, and we will upload them on the platform, which will be open to all. Next. Yeah, and as we said that our target groups are academic staff, students, also customers in electric and hybrid cars, and also employers of vehicles enterprises. Next. And as we said that we have a continuous quality for the projects, which is led by our partners in Greek, and therefore please at the end of this workshop evaluate it, because this evaluation is very important for us. Finally, this about disseminations, we'll have like many activities about disseminations, and also we'll conduct some info days. We have also project website. Maybe you can also enter to this project website and check the information that we have at the website. This is the website. Maybe you can find here. We have also a Facebook page. In addition, we have also a YouTube channels, and also maybe some workshops is uploaded there. So this is like a brief. I was tried to be a little bit faster to like cover most of the works that we have. And as I mentioned that, thanks again for Professor Ajib and for the team at the Ostwestfalen Libe. And hopefully that will have like enjoyable workshops in this rainy and cold weather that we have today in Jordan. Thanks.
Thank you, Professor Ahmed, for your brief introduction of EcoCar project. So please allow me to introduce you Professor Salman Ajib from Ostwestfalen University. His presentation will be regarding hydrogen vehicles, state of the art and perspectives. Professor Salman will be with us for 1 hour. So please, Professor Salman, the floor is yours.
Thank you very much. Thank you, Professor Ahmed. Thank you, Engineer Sarah, also for our organizing these workshops, which I think are very important for successfully of our project. Also from my side, good evening, everybody. I welcome you to our presentation, our workshop, which includes 2 presentations, as Professor Ahmed and Engineer Sarah said. The first presentation is about hydrogen cars, which are actually a type of or a kind of hybrid cars. And I hope the presentation will be interesting for you. Please, can I take the picture? Yes, yes, son. Like small moment, I will my brain, sorry, I have to, is the screen free, or can I now? Can I load my presentation?
Yes, you can. Please, can you share it now?
Yes, thank you, Mama. But I don't see my. No, that is not. Maybe here. Yes, here. So yet now.
Yes, we can see your screen
yes,
now.
Yes, I think now that is not the beginning, and I will make as slides. So, okay. No, so can you see my screen now?
We are just seeing the files. We don't see any presentation.
Oh,
Maybe you can stop sharing and sharing again.
yes. So I hope now is now okay.
No, we don't see anything.
No, sorry. Okay, I will make it as I will make so, and again sharing to the that is the way I so by me actually is.
We can only see the files. Can you just open it, please, Professor Salman?
Yes, I opened actually.
Salman,
Yeah.
can you send it to me?
Yes,
Then I can open it.
but why it is also see?
Yeah, it's difficult.
Nee, aber also Bildschirm freigeben, das habe ich eigentlich gemacht, Sabina. Und warum kommt nicht das? Ach ja,
Muss die richtige.
now I think now.
Okay.
Now, yes. Yes,
Is
now
yeah,
it is.
okay. Because okay, good. Because I so and okay is now okay.
Perfect. Perfect. Yeah, thank you. You can
Thank
start
you very
your
much.
presentation.
Thank you very much. As I said, the presentation is about hydrogen vehicles, and this presentation made with my assistant and the student, Mr. Henrik Harmeling, also, and he is master student and scientific assistant by our university, or by me in my department. So, second, the main points what I want to speak about is small or a short introduction about the importance of hydrogen vehicles in reducing CO2 and in increasing the using of energy efficiency. Then I will give a short explanation about the function principle of hydrogen vehicles. After that, I will speak about working principle of fuel cells, because they are here a part of the hydrogen vehicles. Then I will give a short maybe presentation about state of the art worldwide about the using of hydrogen vehicles in different types. Then because hydrogen is the main fuel for driving of hydrogen vehicles, I will speak about the possibility of production of hydrogen. Then after that, I will speak about storage of hydrogen, transportation of hydrogen, refueling station and hydrogen, security measures, because that is also very important topic. And after that, I will speak about total cost of ownership hydrogen buses. And at the end, I will give a short overview about basic of using of such cars or vehicles.
نصلي المغرب معكم.
Sir. That is the state or the conventional cars make, yes, a great emission of CO2 and other pollutants. And of course, we don't want to less this situation. So therefore, there are many possibility to avoid the CO2 emissions from cars. And of course, e-car and hybrid cars and hydrogen car are promised issues or promised technology to decrease actually these pollutant emissions, CO2 and another pollutants. Worldwide, the transport of transport vehicles make CO2 emission about 8 billion metric tons. And this account about 24 of CO2 emissions from the energy sector. The total emission as CO2 emission is about the amounts about 34 billion metrics. From these, as I said, 8 billion are from transport vehicles or devices, and from these, about 6 billion metric through the total, that means for passenger cars and for cargo. And in details, about 3.6 billion metric tons CO2 from passenger cars, and about 2.4 billion metric tons from cargo. And the total, as you see here, worldwide emission from transport is about, as I said, about 45 from passenger cars, about 30% from cargo, heavy transporter, about 11.6 aviation, shipping has about 10.6%. Rail, you see here, railway is very, very small percentage because many railway are electrified. As that means the rails, most of the railways use electricity as drive energy. Other about 2%. Now, how can we tackle the net zero emission goal? Either stopping the driving internal combustion engine vehicles, that is of course not possible, at least in this time till now, or we have to shift the technology to other possibilities, to other drive energy sources, and these are or could be biofuels, battery electric mobility, which we aim actually to use, and fuel cell electrical vehicles. What we actually the two last options are included in the objectives of our project. And we hope that at the end of the project, we can, yes, provide some, at least some information and some courses about the possibility of use these two technologies in the, yes, in the near future. So now, what is the function principle of hydrogen vehicles? You know that as we need hydrogen tank, hydrogen supply system, and of course, the heart of the system is the fuel cell stack to produce either electricity or hydrogen if it is needed. How can this realize it? You know, fuel cell needs air, also oxygen, also the oxygen and hydrogen supply, and through electrical energy, or can this, when we take this possibility or this process, then the fuel cell can produce current also to charge batteries, and of course, as output, we have water and heat. Now, we produced the current to charge the battery, and this battery can then, through a power control unit, can drive the electric motor of the vehicle. So that is the diagram or the sketch of the diagram of the hydrogen vehicle. And now we found actually this function scheme as as components in the car. And as you see, the heart of this process is the fuel cell stack. We need hydrogen tank. We need oxygen, of course, from the air. Then we have our battery pack. We have our electric traction motor. Then we have the transmission system, power electron controller, then DC to DC converter, cooling system, and of course, for all cases, we need auxiliary battery if the system maybe cannot be work because for a reason or for other reasons, then the car has an auxiliary battery to be driven or to drive the motor for a short way, or to be able to go to the workshop where can the car be prepared again. So how can the fuel cell work? As work principle, I think for many of you is clear, but I want to present the work principle in short, shortly. As you know, here we have the fuel cell have two important anode and cathode, and we have electrolyte here in the middle, and the proton exit. Of course, we need hydrogen and we need oxygen, which we can take from the air. And when the proton exchange membrane, that is here in the middle, the reaction occurs as following: as the anode supplied hydrogen catalytically into protons and electrons. Yeah. Then the protons pass through the membrane to the cathode. Yes, here. And electrons create a current output with an external load circuit to the cathode. As you see, that is our electron flows. And oxygen molecules react with the proton and the electrons. And at the end, we have here water and heat. So now I want actually to make more details about the work of the polymer electrolyte as example for electrolyte material, only as example. In this membrane, the electrolyte is a solid, specially plastic material for the fuel cell. And in this case, water, that is our water here, reacts at the anode to form oxygen and positively charged hydrogen ions. That is our protons. So as you see here, we have oxygen plus 4 ions, and as you see, the reaction is water will be split to oxygen and hydrogen positive. So the electrons flow through an external circuit, as we see here. And the hydrogen ions selectively move across the polymer electrolyte membrane to the cathode. Here. At the cathode, hydrogen ions combine with electrons from the external circuit to form hydrogen gas. And the reaction, the two reaction equation, as you see here, also anode reaction, that is our here, water will be split in oxygen and hydrogen plus 4 electrons, and the cathode we have the hydrogen plus the electrons. Then we have, or as a result, we have our wanted or wished hydrogen. So now about the state of the art worldwide. As you see, we have worldwide about 35 fuel cell electro vehicles, and these are distributed in about 26 vehicles as passenger cars, and about 5,600 buses, about 3,000 medium duty trucks, about 50 light commercial vehicles, and heavy duty trucks, about 14 pieces. Now, it is very important to know how is about the needed fuel. That means the needed hydrogen for the different types of the cars or of the vehicles. And this build or this picture here firstly shows the distributing or the manufacturing of such vehicles, passenger vehicles over continents. You see here in ASEAN, actually China is the most, Japan and South Korea are the main manufacturer of such vehicles. In North America, about 9,300, and in Europe, about 2,400. So now the different types or kinds of the vehicles you see here range per fuel tank as limousine, Toyota Mirai to about 650 kilometer. Actually, yes, here. And as a full tank, does that means this 650 kilometer can, or the car, there's a vehicle can be driven for 5.6 kilogram hydrogen, 650 kilometer. The specific, in this case, the specific fuel need in kilogram per 100 kilometer is about 0.86. The other car, also SUV, that is actually a special car for, yes, high technology or high comfort. You see the specific need is about 0.84. And Honda Clarity fuel cell as limousine is only 0.77. And against to that, the Mercedes GLC fuel cell, although this is also a comfortable car or vehicle, but it needs, as you see here, more, also somewhat more than all other vehicles, about 0.9 kilogram per 100 kilometer. So that is actually a picture what you see in our poster. That is Toyota Mirai 2. And for all your information, I wanted to show you the two most known hydrogen cars, Hyundai Hybrid SUV and Mercedes-Benz KLC Hybrid. So what about the buses? That means the big vehicles. The total amount of these are worldwide. The number that is in 2020, that means actually the static or the day, it is updated only to 2020. One has about 5,300 buses. The most are located in China. The major original equipment manufacturer are Foton AOV in China, Tsinghua Yutong Bus in China also, Toyota in Japan, and Hyundai in South Korea. As you see here, the topic of buses or buses of our continents, the most amounts is in ASEAN, also North America is about 64, and in Europe, the number is relatively actually low. That is some pictures from the hydrogen buses. That is here, Yutong, as only for impression. That is the different manufacturer, and you see actually the buses are very good or are very wished, especially in the transport of touristic or a big number of public pupils. So also in the trucks, also heavy transporter, there are some vehicles which are driven with hydrogen, not zero emission, powered by green hydrogen. So now we spoke about the importance of hydrogen vehicles and the state of the art, and because hydrogen is the main fuel for such types of cars, we have to know how can we produce hydrogen. There are many types of hydrogen. These types are green hydrogen. The source is renewable energy. Blue hydrogen. The source is natural gas plus capturing of carbon. Storage systems. Gray hydrogen, natural as source is natural gas. Sorry. Black and brown hydrogen, source is coal and sorry. Lignite, pink hydrogen, as source nuclear energy, turquoise hydrogen, natural gas plus pyrolysis, yellow hydrogen energy mix. It is yellow because here we have energy mix. That means we have renewable energy, we have energy from carbon, we have energy from nuclear, therefore it is energy mix. And white hydrogen is through fracking. That means through earth shooting. That is hydrogen reserve in the earth. So I don't want to explain every part of these possibilities, but exemplary, I want actually to show you the possible amounts of hydrogen and what as output and as input, what we need in these three examples here. As example, when we take the streaming of methane reformers and water, we have to have example here 1,989 kilogram methane and about 4,468 kilogram water, and we have to supply with 5.7 megawatt hour. In this case, bekommen wir 1,000 kilogram hydrogen, and the other is CO2, which is either can be again used for, as example, producing of methane, or for other perspective or other method purposes or other purposes. Or we can take the electrolysis, what the fuel cells actually used. Then we need, as example here, electricity as energy source, about 30 or 40 megawatt hour, and this energy can supply, or the water that means can supply about 9,000 kilogram water to produce at the end about 1,000 kilogram hydrogen, and the rest is oxygen, about 7,900 kilogram oxygen. The third method here, methane pyrolysis, and in this case we need only energy and methane. And you see here, this methane through inner heat can be distributed in or converted actually in about 1,000 kilogram hydrogen and 2,900 kilogram carbon. So exemplary, I want to only to explain in more detail the production of hydrogen through steam methane reforming and pyrolysis. In this case, the steam methane reforming is a process requiring high temperature and pressure. That is the first stage. That is in this case we need methane plus water. Then as a result, we have CO, coal monoxide plus hydrogen. In this case, we have about 206 kilojoule per mole. And for that, actually, we need high temperature. Therefore, here, the process required high temperature, and this temperature is about 700 to 900 degrees centigrade. In the second stage, the coal monoxide can react with the water again to produce CO2 and hydrogen again. And in this case, we need energy, heat, with about a specific heat, about 40 kilojoule per mole, and the temperature is about 90 to 230. That means here actually this case, in that means that is our possibility. We have here methane and heat, then we have hydrogen and carbon. That is what we have at the end. So during this process, also hydrogen is generated in reactions 1 and 2 with methane and monoxide, also carbon monoxide, and water participation under pressure. From the pressure, the needed pressure is about 15 to 30 bar, and the equipment must be actually must be against or able against Earth. That means the material must be resistant to the high temperature and to the temperature shift between the first and second stage. Yes, because we have here 700 to 900, and then in the second stage, the temperature is only about 90 to 230. And in this case, maybe the material can be expand or expand. And the material must be resistant to this exchange. The process requires nickel or nickel alloy catalysts to avoid catalyst poisoning. The gas needs to be desulfurized, as it is not allowed to have sulfide. The conversion efficiency of fuel to hydrogen is about 65 to 85, according to the process parameters. So that was only as example, and the other part or other kind of energy of hydrogen production, I will only mention the possibilities. Also gray hydrogen, we need natural gas or methane. In this gas, in this case, the steam methane reformation. That means we have to reform the steam methane. Then we have black and brown hydrogen. That means we have to gasificate the black coal or lignite. Then we have the blue hydrogen from natural gas through steam reforming with carbon capture and storage. I mentioned it before. A green hydrogen, that means it is therefore green because we need here, or we use here, only renewable energy resources to produce the hydrogen through electrolysis. No? Then we have the pink hydrogen from nuclear energy through electrolysis. Turquoise hydrogen, we need natural gas through pyrolysis. Then the yellow hydrogen, electricity mix. Also, we need here from grid the current or the energy, and this energy is as mixed from different energy sources. Through electrolysis, the white hydrogen, naturally occurring geological hydrogen with fracking, which is known as earth shooting. So that was about the possibilities of production of hydrogen. And now, what is about the production of hydrogen or the reserve of hydrogen? Worldwide, you see, we have about 70 million tons of hydrogen, which are produced through natural gas. From coal, we have about 21 million tons, mostly in China. From oil and electricity, about 1.9 million tons. secondary product. As secondary product from other processes, we have about 50 million ton as example from fertilizer production. And you see here that is the sources of production of hydrogen. As you see here, natural gas is the most source. Coal is about 23 and oil only about 2%. So now, how can we storage the hydrogen? As due to its physical and chemical properties, costs are higher than those for other energy sources. That is normal because oxygen, hydrogen, we have to storage it under high pressure. Otherwise, we need a very big volumina. And of course, high pressure needs also energy to produce it, but that is possible. Therefore, I will here illustrate or present the most used methods for storage of hydrogen. Also, either we can physical based on compression, cooling, or combination. That means compressed gaseous hydrogen. The needed pressure, as I said, is about till 700 bar. Example in Pekin, Sino Hydrogen, that is the company which use this method. Then we can liquefy the hydrogen. And in this case, we need storage tanks. Of course, we have to make or to have the insulation between the side of the storage tanks and the inlet side of the tanks to make the heat transfer from out to inlet of the storage so low as it possible to avoid the increasing of the pressure in the tank itself. Then we have the cryo-compressed hydrogen, as example, the refrigeration machine of Linde. Then we have the second method, material-based storage. In this case, metal hydrides, as example, Power Paste, that is a research project in Fraunhofer Institute in Germany for manufacturing technology and advanced materials. Or we have liquid organic hydrogen carriers. Example, hydrogen hydrogenous LOH technology GmbH also in Germany, or sorbents, nanotubes, zeolites, research. All these actually this here, these three types in research. It is not known as a big yes mark commercial mark. This it is only research results. So also due to its physical and chemical, it is more that I said that the physical storage methods, compression, cooling, or combination. You see here compressed gaseous hydrogen in a very big and long tubes, or as I said here, liquefied. That is yes, liquefied hydrogen from Kawasaki. Yes, and cryo compressed hydrogen, of course, in temperature, very low temperature, cryo temperatures. So material-based storage methods. You see here the tubes, metal hydrides, power paste as power paste, and liquid organic hydrogen carriers. Yes, chemical storage here, and sorbents as example, zeolite, metal organic framework, or nanotubes. So now, how can we transport the hydrogen? The methods which are used to transport the hydrogen are either as liquid hydrogen, LH2, or through ammonia, and then we can split the ammonia in nitrogen and hydrogen, also in H3, or as the liquid organic hydrogen carrier, LOHC, which what we said here. Yes, and yes, the most promising one until that is the liquid hydrogen, because of the cost, of course. Yes, and therefore it is here the most promising method for transportation of hydrogen. Ammonia is in research, and liquid organic hydrogen can also as research topic. That is globally when we or of course in ships, that is also it is known method for transporting of hydrogen. Locally, that means in the near distances, either we can transport hydrogen as gaseous hydrogen by truck, or as gaseous hydrogen by pipelines, or as liquid hydrogen by trucks. This here also locally and by truck for it is suitable for short distances plus small amount. Gaseous hydrogen by pipeline for large amounts for industry purposes, and liquid hydrogen by truck for distance greater than 300 kilometers. Yes, because in this case, yes, the amount or the mass of transported hydrogen will be more than the case as gaseous hydrogen. So only here as example, I want to see you how can ammonia production Haber-Bosch process through or from ammonia we can produce hydrogen, or in the another direction, against direction. As for this process, we need a pressure at least 200 bar, temperature about 450 degrees, and the catalyst is iron-based catalyst. And this is the equation in two directions. Yes. So now we come to the refilling station of hydrogen. The first step is we have here our storage tank, low pressure storage. Pressure is 220 to about 200 bar. The storage for few days. Here we can store hydrogen in gases, as not liquids, only as gases. Then we can compress through compressor. We have a piston, that means compressed air diaphragm or ionic compressors. Then we have high pressure storage. That means the pressure is 200 to 450 bar or 8 to 1000 bar. used to refuel the customer vehicle. Here, pre-cooling compressed hydrogen heats up, necessary to stay within the boundaries of the storage system. And here is our dispenser. The pressure here is about 352 or 700 bar. So then what about the ownership of these refueling or refilling stations? That is the most are state stations, although about 75 are public stations, and the pressure of these stations is different according to actually this scheme what we mentioned, either by 350 bar or 700 bar or these both. Yes, now about the stations, the distribution of the hydrogen station in total worldwide is about 540 stations. These are in Australia, about 190 in America, is about 71 in Europe, is very small one in Australia actually, that's it in Europe. And in Asia, that means China, the most are in China, about 250 stations. So we come now to the security measures. As you know, the hydrogen station are under a high pressure, and therefore, yes, the security measures must be definitely must be keeps. Also, that means they have to have a very note, a very consideration, a very high consideration. And of course, this picture we don't want to see often. This picture that was explosion in Norway in for 2 years, about 40 years, 2019, and therefore there are many security measures which have to be considered by installation of such hydrogen stations. And of course, the security measures must be considered also by transportation or also by production of hydrogen. So some of these measures use non-combustible materials for the buildings of the refuel station, install hydrogen sensors at the exhaust of the tank, station, and the car, avoid ignition sources near the storage area. If a fire or leak is detected, an automatic shut-off is activated near the storage system. Classified electrical equipment should be used. Mechanical ventilation to decrease the likelihood of flammable mixture. That means it must be, or many ventilator must be usable by the dangerous. If an explosion has done or occurs, the fire, yes, avoiding devices must be take in work, and also when it is possible, mechanical ventilation must be also take in operation to decrease the the possible incidents or accidents in the station or in the building. So now we come to the economic side or economic part of using of hydrogen vehicles. What is about the economic, the needed investment or and the needed money or cost for the operating of such hydrogen vehicles. Now, also, yes, based on a total cost of ownership analysis, subsides are ignored in this case to see what is the basic of our calculations. Also, we haven't here subsidized possibilities either on vehicle purchase or fuel, and purchase and operation costs for 2019. You see here in China as the cost per 100 kilometer for fuel in China is about $178 per 100 kilometer, and in Europe about yes, 190 is somewhat more. That is low. That is yes, I think reality, but not very more. Purchase price in percent is here 31 and here 32 from the total price. And operation cost, yes, about 70%, in Europe, about 60%. That means, yes, based on total cost of ownership, that means here in purchase price, $1,000 per vehicle. You see here in China, that is depending of kind of the vehicle. Here, fuel cell electric vehicle. You see here about 314 or 15 $1,000 per vehicle. In against to that, by ignition combustion electro vehicle is about only 77,000. And in Europe is about double yes, double as in China in both, yes. And operation costs also are in China somewhat yes, here higher than in Europe because of the yes, providing of the components for the vehicles. And here is in Europe again higher than in China. The break-even in China, break-even for injection combustion vehicle is estimated to be 2077, and in Europe is yes, 2024.
Professor Salman, I just
Yeah.
want to notify you that we have only 3 minutes.
Yes, okay, thank you very much, because I speak and,
Yeah.
and okay, I can here make faster. So now purchase cost, you see here that is, yes, depending on the manufacturer, on and where we purchase these vehicles, that is in China, fuel cell electric vehicles. As example here, cluster profiles, 16%, also other components, 19%, 15% is for components make up, mark up, also energy module and drive and train. That is depending on really on the where we purchase these vehicles. If you want, we can discuss about these distribution of the parts of the costs at the list at the end of the presentation. Again, here purchase costs depending on the country or continent, and as you see here in Europe is other components about 35%, components mark up 30%, energy modules 20%, drivetrain self here is very low, only 10% and 14% for cross profile. So operation cost, of course, depending on the costs of the hydrogen and its production. And yes, you see here we have fuel, we have charging station, maintenance, parts replacement. That is very important, and especially in China, we see here that is about 21%, and insurance here is in Europe about 15%, and against to China is only about 7%. No? Good. Here also operation cost again, depending on the operation cost per 100 kilometer. So then, yes, I come to the last slides, perspectives of using of hydrogen vehicles as a fuel cell, decrease manufacturing costs that is needed to make the spreading actually of hydrogen vehicle is possible and economic, and increase efficiency, also long-term stability, support technology acceptance, as good as the used product powered by fossil fuel, expand the infrastructure with the long-term goal of nationwide coverage, cost competitive, then encouraging carbon natural production of hydrogen with an increased installed capacity. In China, it is planned to make also about 100 gigawatt by 2030. In Europe, about 80 gigawatt initiative. In Germany, directly about 5 gigawatt by 2030. There are actually, I want to only to say in this regard, in Germany, they the topic hydrogen and hydrogen production as either as for transport or for other industrial process or as energy carrier. It is very important. For about 1 month, we had a conference for 2 days only about hydrogen and hydrogen processes and how can we, cost and effective produce hydrogen, how can we transport hydrogen, as example, from us, Australian to Germany. There are agreement actually to make cooperation at this field. It was very interesting. The ambassador of Australian has that had made a very interesting presentation about this possibility and about this cooperation agreement. Also the research about the decreasing of the costs was a very important topic in this conference. And of course, the conversion of power to gas and gas to power was an important topic at this conference. And of course, especially the power to gas, that means power to hydrogen and hydrogen to power was very interesting and had many presentation actually, or it was many at this conference, many presentations have been illustrated at this about this topic at the conference. So that is some sources or the references which have been used in this presentation. And yes, thank you very much for your attention, and I am pleased to hear your comments or questions. Thank you very much again.
Thank you, Professor Salman. Very interesting presentation and also very interesting topic. Now, hydrogen is one of the main highlighted topics in hydrogen, in energy, especially green hydrogen. And Jordan now is one of the main hubs for adopting green hydrogen in the near future. So thank you again, Professor Salman. You have like enriching our background regarding hydrogen, green hydrogen, and especially in the transportation sector. So regarding the workshop, I just want to notify you, please, to evaluate our workshop. The email, the link will be sent again through the chat. Now we will move to the next presentation.
Okay.
And if you have any question to Dr. Salman, it will be like in the discussion session. Yes, Professor Salman, would you like to add something here?
Yes. Should I stop the presentation or I will?
Yes, please. Yes, please.
Yes, with pleasure. Yes, yes. Okay.
Yes, please. Thank you. So yeah, great. Thank you. So our next presentation will be by Dr. Sabine regarding charge transport in batteries. So Dr. Sabine, the floor is yours. You can start now your presentation and share your screen.
Thank you, Sarah. Thank you for introducing me. Yeah. And thank you, Salman, for giving me the opportunity to participate in this workshop. Thank you all for joining us here. So first, before I start, I would like to tell you I'm not working in the research part of the university, but in the Research and Transfer Center. So my main I'm mainly in charge to support proposals, research proposals, but I tried my best to compile some facts about charge, transport, and batteries for this workshop. So I will now share my screen. I think I should be able to see my presentation. Okay, very good. So the next slide, you will, I give you some facts for the charge, transport, and batteries. And I'm not quite sure if I really met the target group here. I'm not sure if you're researchers or if there are some students. So there may be quite a different level of information. So what are the requirements for batteries in electrical vehicles? So it is commonly agreed that we need an energy density of more than 750 watt-hours per liter. So that's some data for the volume of the energy density per volume. And we need more than 350 watt-hours per kilogram. That's the watt-hours per weight. So both of this is important. So the volume, of course, can increase the space that is needed by the battery, and the weight makes the battery less effective if it's very if it's very heavy. Currently, the current batteries, they are all below this ideal, this minimum requirements. So what's about the costs? The battery should be less expensive than $100 per kilowatt hour for the cell. Currently, the packs, they are more than 200 kilowatt hours per pack. Or I think it's also, it's not, it's for the complete cell and for the complete pack. It's the same, should be the same here. We need a fast charge and power. That means 80% state of charge, SOC, should be there in 15 minutes. Currently, we need several hours to charge a car, to charge the battery of the car. The life for the battery should be 15 years at least, so it's the same as the lifetime for the car. Because the battery has to be, when the battery has to be replaced, you should currently, in the current systems, the whole car will be replaced. So the lifetime for the car is the same as the lifetime for the battery. So the goal currently is 15 years. The power capability differs for the vehicle type. So you need another, a different battery if you have a van or a large vehicle for transportation than in a personal car. So and usually you have the compromise between cost and energy density depending on the vehicle type. Yeah, the performance should be that there is minimum impact by the environment. So what means the temperature, the water content of the air should be all compatible to the battery and should not lower the performance. There should be, there's also the safety issue. Flammable and fire catching batteries are not desirable, of course, and there's also sometimes the risk of rupture or explosion that should be avoided in the batteries, of course. So what kind of battery types are used for electrical vehicles currently? Very common is the lithium-ion battery with high energy densities above 250 to 693 watt hours per liter and 100 to 65 watt hours per kilogram. That is still significantly less. This is still significantly less than that of gasoline. No, that of gasoline is it's not less than that of gasoline, still higher, but it should be significantly less than that of gasoline. So there are next generation batteries that are needed with these higher densities per liter and per kilogram, but they are currently still under development, such as lithium sulfur, lithium air, or magnesium ion batteries. There are still some research done on lithium metal anode batteries, but all these batteries are currently not available with sufficient energy density for the overall system. And there's one word about this lithium metal anode batteries. They are currently not considered very safe, because when the lithium is exposed to humidity and air, if the battery breaks, then you will have a catastrophe. Then the lithium will, of course, react with water, and this battery will catch fire. now I come more to the transport of charges in these batteries. In principle, a battery or accumulator is built of a stack of galvanic cells. Now let's have a look at this galvanic cells. A very simple galvanic cell is built of 2 electrodes that are lowered into an electrolyte. This electrolyte can transport ions, ion charge, and also mostly ions that are in a solution in this electrolyte. This electrolyte can be liquid. It's usually liquid. Can also be a molten salt. If you divide this 2 parts for each, if you have a different electrolyte for each electrode, then you have 2 electrodes, two halves of one complete cell, or you can also say 2 half cells. Yeah, for example, one zinc electrode and a copper electrode. You need to connect these electrolytes by maybe a salt bridge, or you can have maybe in the middle a porous membrane, some porous contraption that allows for the exchange of ions and of cations and anions, so that the electrons can still flow in the outer circle. If there's no charge transport, then the electron flow will of course stop in the outer circle, and the battery will not work. But if you have a connection, then for the exchange of charges, then this battery is functional. Good. Next one. Then you can have a look at the electrochemical series to see which voltage will be produced in this cell. You see this very popular lithium ion battery has a very favorable normal potential of -3 and 0.3 volt. Therefore, this is this materials with a very that are very high here, and this electrochemical series produce higher voltages when combined with other materials which are on the lower side of this series. But I think you all know this. So now I come to the Nernst equation that is used to calculate the voltage. You have for the half cell you calculate the this voltage by the normal potential, the complete potential. You have the normal potential at certain temperatures, certain concentrations, and here you have a correction factor for temperature, the charge number, and the current actual concentration in the for oxidation and reduction. There are some special cases. If you have only a metal electrode, and then you have this simplified equation. For non-metal electrodes, there's also a simplified equation you can see here. Sometimes you don't, you have an overvoltage, which means that the battery is not working as you need, as you want in the desired fashion. This occurs when all steps of the reaction are fast, but they slow down to high diffusion times of the electrodes. If the ion needs a long time to diffuse to reach the electrode because of diffusion hindrances, obstacles, then then this battery is not working as desired. even, yeah, if you have very mixed electrolytes, there's this stationary boundary of thickness 10 to 100 micrometers that does not move, very close to the electrodes. This is the diffusion barrier. And yeah, his equation that applies to this diffusion obstacles. Okay, I can go to the next slide. Regarding the electrode kinetics, that's the speed of the process at the electrode surfaces. There are individual steps for an electrode reaction that can take place even in a battery. So the diffusion of the substances involved to the electrode slows down the process, is one step in the process. There's a possible reaction in the layer directly at the electrode, so that also a very undesired reaction can take place, like plating of the electrode done by lithium. You have absorption of the substance on the electrode that is sometimes desired, sometimes not. Transfer of electrons via the electrode, a desorption or detachment of the substances from the electrode, so that you have the charging process and you have the decharging process, and in all these processes you have to also look at the electrode kinetics that are influencing the overall reaction. There are also sometimes reactions in the boundary layer if necessary, or the rediffusion of substances in the electrolyte that can take place in the charging and discharging of batteries. If you look at the ion mobility of the current transport of the actual transport of ions within the liquid electrolytes, you have quite simple, really quite simple equations. You of course expect that large ions will be drifting slowly and have low conductivities, and the drift velocity you can calculate by drift velocity is ion mobility times the field strength. And two forces are there acting on the ion. One force is the field, the electrical field, the number of ion charges times elementary charge times electric field strength on the one side, and on the other side you have a force acting against this field force. This is the retardation force, 6 times P times the viscosity times the radius of the ion times the drift velocity. When the drift velocity is reached, then both forces are equal. What you see here in this equation, Z times E times field strength divided by this term here. So the ion mobility can be identified by the drift velocity divided by field by the electric field, and but on the force by the potential. What's equal to this term. You can calculate an ionic conductivity. This times sigma plus minus can be, so you can calculate this conductivity for the cations, and you can calculate it by the same equation for the anions. That is this number of charges times electric field strength times ion mobility. Oh, no, sorry, not the field strength, but the Faraday constant that is given here in the last So sorry. The ion mobility is high for an ion that is highly charged, like here the calcium ion. It should be a plus. I think it's not really. These are all cations. It is high in a solution of low viscosity, of course. It is directly in connection to the equation from the last slide. It is high for an ion of small radius, but you should take into account that the radius is not only not only for the ion itself, but some ions they have water ligands around them, like the hydrogen ion, the proton. And therefore, you see the ionic mobility of the proton is yes, different than from other ions here, because the proton is transported by the Grotius conduction mechanism, where that means this proton is hopping from one H2O to the next one. Therefore, has a different different transport mechanism. This is more important to the for the hydrogen cars, which were the topic, the subject of the talk before me. But for the lithium batteries and other batteries, of course, these ions are more important. If you look at the ion mobilities and conductions at solid electrolytes, it's a bit different from for liquid. You have different equations from the liquid electrolytes. For example, when you look at a direct current, what is the important current modus for the solid state batteries? Then you have an Arrhenius type dependency on the temperature of the conductivity. In some materials, especially in the disordered materials, which you have in the membranes that are separating the different reaction chambers in batteries, there you have this kind of a little variation of the Arrhenius type dependency. What you also can do, you can look at the AC conductivity. I think it's not so important for our batteries, but still you should be aware that we have different dependencies on frequency, on the temperature, and of course of the frequency dependency. Yeah, there are several models for the AC conductivity, but I think still currently there's much research on this done. If you have plot this conductivity against conductivity times time temperature against the frequency, you get dependencies like this. Here you have the so-called direct current conductivity. This is the important current conductivity of our batteries. And you see here this Arrhenius behavior. You have you can draw a constant a line, but yes, it's only for illustration. If you have a look at the lithium-ion battery that are currently used in cars, some of the batteries, they really look like the battery you know from your home use. They have a cylindrical, especially the Tesla cars. They're using, I think they're still using 7,000 of this cylindrical batteries. That's curious, but yeah, I think that's still state of the art. You see how they are built. They have this steel plated positive cover. And on the outside, a metallized PVC label or outside. A cathode made of manganese dioxide, carbon, and some an electrolyte. Next layer is the separator, separating the two the two reaction rooms. It can be a non-woven fabric, and of course we need an electrolyte to make the charge exchange possible. The next one here is an anode gel, sometimes with powdered zinc. And let's have a look. Then here's the current collector in brass in this type of battery. We have a metal washer, an inner cell cover, also made of steel, and a seal made of nylon, so that there's no contact between this steel-plated positive cover and the other cover outside here. Yeah, most of the other cars, they don't use the cylindrical cells. They have pouches instead. On some industrial applications, they also use another form factor. This cylindrical form factor is not the best, I think, for because it's not easy to have a very density pack. So most of the industrial use and some of the electric cars, they use pouches like this. If you have a closer look at the principle of the lithium-ion battery, on the one side you have here the aluminium current collector at the cathode. Here's the charge functionality. Here you see lithium metal oxides and the lithium intercalated between this metal oxides. Here's a separator to separate the two reaction compartments. But the separator is, the lithium ions can move through the separator, but other ions are not able to pass through the separator. On the other side, you have this copper current collector. You have carbon black or some other graphite, and in between this graphite or carbon black layers, there you find intercalated lithium ions. During the charge time, you see electrons are transported to this anode, and here on the other side to the cathode, and in this direction to the left, lithium is transported to the right side when the battery is charged. When the battery is discharged, the flow is on the opposite. Electrons are transported to the right side, and lithium is transported to the left side. Okay, so that's the very rough principle of the lithium-ion battery. So lithium ions transferred from cathode to anode during charging, and their speed is controlled, of course, by the intercalation rate and the diffusivity of the lithium ions. If I have a high charging rate, the lithium plating and anodes at the anode surface, and this is taking place, and the cell temperature increases rapidly. If you feel that your lithium battery is getting very hot, then it's not a good sign. That means that some degradation is taking place. So-called lithium plating. So you get lithium directly on the electrode, and that's not the desired place. You want your lithium intercalated in your material, this materials, the oxides and the carbon. So this high charging rate can induce reduced capacity, reduced life, and of course reduce safety, because the cell is getting very hot, and there's this risk of catching fire, of explosion. So there are some attempts to increase the charging rate by pre-warming of the cells to improve the electrode kinetics. Also the electrode kinetics of, as I said, as I demonstrated before in the equations, they are influenced by temperature. If the temperature is higher, then of course the kinetics are improved, and we can charge with higher charging rate. We can employ a higher voltage system to reduce the current level of the battery, or we can optimize the charging algorithms that allow fast charge without impact of battery life and safety. There are also some methods to cool the battery down. There are many of the lithium ion batteries, they come with cool packs, and these cool packs are coupled to a charging algorithm, so that when the battery is getting hotter, it's getting more warm, then this algorithm can use it to cool the battery down. So what is now the impact of lifetime? What are the degradation mechanisms? So there's one is that we have this growth of a solid electrolyte interface that's not desired. We want to have the electrolyte interface that was originally built into the lithium battery, but we don't want the growth of this solid electrolyte interface. What we don't want is this lithium plating that occurs by when we charge with high rates and the temperature is increasing. There's also some lithium ion loss at places where it cannot be replaced by the charging process. And sometimes we have a completely uneven distribution of the ions with, uneven distribution of ions within the electrodes. The electrode volume can change due to intercalation. So if we have intercalation of ions in the electrode itself can grow. So that's also not desired, and you have the battery pack will increase in volume. Sometimes you have, of course, the companies they take measures against this electrode volume increase. They apply pressure from outside to keep this battery pack in the desired volume, but nevertheless, sometimes the pressure from the inside is getting too high. And sometimes you have gas formation from side reaction that are not desired, and also this gas formation can increase the volume of the battery or the electrodes, and what can follow is a rupture of the battery. Environmental conditions are very important. So the performance of the battery, the charging rates, and the degradation is of course affected by the temperature, as said before. At high temperature, we have a high charging rate, but this increased solid electrolyte interface that is not desired. This will grow, and also some other undesired side reaction will take place. At low temperatures, this low temperature slows down the solid electrolyte interface growth, but instead the lithium plating occurs. That is also not desired. Batteries can of course be optimized for higher, either for high or low temperatures, but then this optimization is only for one temperature. But what we know is our electrical vehicles, they may experience different environments. So to maintain maintain battery performance under different conditions, it is very important to have a look at these different environments that can be experienced by the battery. The optimization of the thermal management management design is needed, especially for the batteries of growing energy density and fast charge capability, especially for this for this desired batteries, we need more optimization and difficult thermal management. Now I already come to the end of my presentation. A lot of research activities are currently going on all over the world to mitigate thermal runaway and other obstacles. There are novel battery materials developed in several research institutions in Germany, in Europe, in Asia, in the US. Yeah, but when we look at all these novel battery materials that are currently under investigation, the cell performance is in the most cases is not optimal. Aqueous electrolytes, for example, are non-flammable but small. They have a small electrochemical stability window. Solid-state batteries, they have high mechanical rigidity, but high interfacial impedance and poor cycle stabilities. I know that some German research and technology organizations, they are still working on lithium anode batteries that have many safety problems. But there's one general observation that we can currently that is currently made in the research fields. The German electric vehicle companies, they work together with several research and technology organizations, mostly in Germany, but also in Asia. They're mainly working on an LG Chem battery, and in contrast, Tesla, one provider is currently building electrical vehicles. They still using Panasonic batteries. So there will be a race for the best battery. I think mainly between LG Chem and maybe Panasonic, but we have to see how this research work will develop in the next years. And then we see if Tesla will also go for other batteries or still use this cylindrical or some other batteries developed by Panasonic. So thank you very much for your attention.
Thank you, Dr. Safin. It was a great and interesting presentation. Then our last presentation was charge transport and batteries with Dr. Safin. Would you have anything else you would like to add here? Yeah, Dr. Sabine, would you like to add anything here?
No, I don't like to add anything here. If there are any questions, of course, we can go into the discussion a bit early.
Yeah, so please, anyone have a question, please feel free to open your mic and ask, or you can raise your hand. We are now opening the questions session. Any questions, please? Yes, Majid Sweti. Please, you can open your mic.
Thank you very much for your presentation. Truly, it's very important and it's clear. But I have a question. My question is, there's a difference between the state of charge and state of power, state of health. If you have to explain the difference between all gauges or all measures that explain the state of battery.
Oh, sorry, I'm not. I didn't get the question completely. You mean no, can you please?
My
again?
question is, I need to make compare between the state of health or state of charge, state of power for batteries. How to check this? The state. Yeah. Is it clear now?
Yes, it's clear. Yeah, I think you have to of course, apply different measurement, different measurement tools to
state of health.
So state of health, you can have a look at your battery. If there's a volume expansion, you can of course measure the temperature. You can measure the voltage. If you only get 80% or less than 80% of the initial capacity, then of course the health of your battery is not so well. That also applies to the state of power, and the other one was the state of health, the state of power, and
state of power and state of health, state of charge.
State of charge.
Yeah.
Yeah, state of charge. Sometimes you can, of course, measure it by the voltage that you get from a battery. If the battery is very low in charge, then you gets not the desired voltage, and you cannot get the desired current. If you measure the current, that's
So is it answered now, Mr. Majid?
Yeah. It's okay. Yeah. Thank you very much.
Thank you so much for your question. Any other questions, please raise your hand or you can open your mic. Yes, Mr. Bilal Jarrah, you can open your mic.
Hello, thank you all for your presentation. Actually, my question goes to Professor Salman regarding the hydrogen vehicles. I see from what you present, the industry of hydrogen vehicles still, I think, too cost, much more complex than electric vehicle. And from what I understand from your presentation, the problem will be in producing and storing hydrogen, which is in the process you show us to produce hydrogen. You also include there will be carbon dioxide produced. I think this will be a big issue if we turn toward the hydrogen vehicle, which is the CO2 always become a problem for like environment and all these things. We are trying to go to green vehicles, not participating in producing much more carbon dioxide, if I'm understanding correct from your presentation.
So, thank you for your question. Yes, only by one method, that is actually the that is pyrolysis was the one method that we methane that we can disturb convert methane through supplying with heat in carbon and hydrogen. That is one method. We can also CO2 as which is produced again in methane, but of course in chemical method through a power to gas method. We can either use this produced carbon as carbon dioxide to produce again methane and hydrogen, or of course by vehicle cars, when we really use this method to produce hydrogen, it would be go in the environment, and that is not the aim actually of using this method. Therefore, I presented the different methods to produce hydrogen, but what we will make with the products of the process, I haven't said what that was not the part of the presentation.
Okay, thank you for your answer. But still, again, if you could give me one more question about if we want to make like a quick comparison between the hydrogen vehicle and electric vehicle, not the internal combustion engine. Yes. I see from your presentation, the gap will be very big in the costs currently. I don't know in the future.
Yes, but the research at this field actually is very accelerated. Also, it's very important, and many institutions actually make many research at this field to reduce really the specific costs for these vehicles, or in generally to reduce the specific costs for production of hydrogen in generally. as I mentioned, it was really here in Germany for about 2 months, a conference only about using of hydrogen and production, transportation, applications on. It was about 50 presentations.
Okay, thank you.
You are welcome.
Thank you, Mr. Bilal, for your question. Any other questions, please feel free to raise your hand. Yes, please.
I would like to have one question for Dr. Salman.
Yeah, please.
Yes, please.
Thank you very much. Good evening. You did very nice presentation. I would like to ask you your opinion regard what is better to use a car with photovoltaic, which means solar energy, or use cars with hydrogen power. As my colleague Dr. Bilal, he said that, and as you explained, that hydrogen will we have like combustion with carbon dioxide, so we will have return back for the problem of fossil fuels with the environment, with the pollution, contaminated, etc. So do you think that using a car with hydrogen will be much better and we will be friendly with the environment than using car with photovoltaic cells?
As I said, that when you allow me, please, to make the presentation, to show you the presentation, it was only possibility. Actually, one, please. So here, so that of course, when we produce or make or convert the solar energy in to charge the batteries, of course the electric cars are very easier and really at now at least cheaper than the hydrogen vehicles. But maybe in the future, when we have yes, when the technology is advanced, maybe the costs, and that is actually one of the tasks of the research of at this field. I will show you some, please. So here, production. Can you see my?
Yes.
Yes.
No, I followed all your presentation. I followed all of it. For this, I did this.
Yes, yes, okay.
All right.
Yes, you see here. Yes, you see only in this here, okay, electrolysis, and by this here, by streaming of methane reforming and by methane pyrolysis. In this case, we have really many part or a big part of carbon. But when we take this method over electrolysis, you see here we have only hydrogen and oxygen. Yes, that is depending on the method which we use to produce our hydrogen. Therefore, that is actually not desirable. This also, but the costs, maybe the costs here of the production of hydrogen maybe will be more cheaper than this year or this year. That is depending on the energy source which we use to produce the hydrogen. There are many methods, and as I said, when we use only this, when we use the carbon not for producing of hydrogen, again, that is enclosed loop, maybe that is environmental, not very, yes, suitable. All this here. Yes, good, okay. Yes, I think, is it clear?
Yes, it's clear. You know what I'm asking? I'm asking from the point of environment.
Yes.
Which one will be more friendly with the environment? This is what was
this actually this method where we use the renewable energies. Therefore, here you see the many kinds of hydrogen.
Yeah.
Gray hydrogen, that is okay, but we have at the end also CO2. The most suitable actually production method is this here, using the renewable energy resources for production of hydrogen. That means the middle one, this year.
Okay. Okay.
Yes, that is the best method.
Yes, thank you very much.
We have here more oxygen and yes, only oxygen and hydrogen, which are both are very environmentally yes friendly.
Okay,
Thank you, Dr. Akram, for your question. Hope it's fully clear.
Yes, thank you very much.
Thank you. Any other questions, please raise your hand or feel free to open your mic.
Yes, I have a question to Dr. Sliman.
Yes, Dr. Muhammad.
Dr. Salman, yeah,
Yes.
how are you doing?
Hello.
Good. Regarding the storage of the hydrogen,
yes,
it happens that I was in a conference, I think 2010 in Clemson University, and there was a group from, I think, Berlin Institution of Technology, and they revealed that they could, absorb the hydrogen inside carbon foam material, and they make it very small with a lot of the quantity from hydrogen, but they faced a problem with releasing the hydrogen, because at that time it was talking about the hydrogen power and the size of the tanks, something like this. But they reached, do you know if they reached to the way that they can release the hydrogen from inside the carbon foam or the porous material?
Unfortunately, I cannot say exactly, but what is where this method is really applied, but I know that is really here in Germany a very big and very big research projects at this field, and by the storage possibilities, I show you that here the possibility over sorbents here.
Porous medium.
Yes, or here also, and these here actually are promised methods for storage of hydrogen, and of course there are methods for release of hydrogen again.
Yes. But if they already did this, it will be very cheap and the size will be very small.
Yes, really here for small metal, I think the metal hydrides are the smallest possibilities for storage of hydrogen.
Okay, thank you very much.
You are welcome.
Thank you, Dr. Muhammad, for your question. Any other questions, please? Do we have any other questions? Please feel free to open your mic, or you can raise your hand.
So in the case that, Sarah, if there is no questions, I think that now we exceeded about 12 minutes after the workshop time, yeah?
And it's already till 6:30, so we are already like before the time, yeah.
Okay.
So if we don't have any further questions, we would like to remind you that we will send the attendance certificate within 2 weeks, and please make sure to evaluate our workshop through the link that have been sent in the chat. Also, we would like to thank Professor Salman Ajib and Dr. Sabine for their great and very interesting presentations regarding hydrogen in vehicles and also in transportation. I would like to give the last word for the project coordinator, Professor Ahmed Al-Salaime, and we will wrap up.
Okay,
you are welcome. Sorry, and only the name of my colleague Sabine.
Yes.
No problem, but only to say the name exactly.
Oh, thank you, Dr. Sabine.
You are welcome.
Yeah, thank you, Professor Ajib, and thank you, Sabine, for this presentations. And as you know, that hydrogen now becomes very important topic. In fact, since 2 weeks, we organized a workshop under the patronage of the Minister of Energy in Jordan. It was with the German colleagues from Wuppertal Institute, from German aerospace centers, and also from other institutions. And it was about the background report related to hydrogen in Jordan. So we started, I think, that our research in the field of hydrogen, and we think that the hydrogen will be like the future energy, and it is very important now, especially green hydrogen. So green hydrogen is very important topic, and I think that there are now many research and many also projects in the field of green hydrogen. Jordan signed the Ministry of Energy and Environment. The government of Jordan signed agreement also with Australian company to build like hydrogen power stations, power plants in Jordan with a capacity of 5 gigawatt, which is huge. And now they have the feasibility study, which will be conducted or started to be conducted soon. So I think that for the hydrogen topic is very good topics to concentrate now, since it is like the future of the energy. We'd like to thank on your behalf our partner from West Westphalian Libre University, Professor Ajib, and his colleagues, also Sabina, for these presentations. And as was also mentioned at the beginning, that they would try also to have such a workshop to be like once per month, and every time we try to have also a new topic related to electric and hybrid car. Would like to thank you all, and please don't forget to also fill the evaluation. And as Sarah told you that maybe within 2 weeks, those who needs the certificate, they will receive it from engineer Sarah. Thanks again, and have a nice evening in this like windy, cold weather, and wish you all the best. الله يعطيكم ألف عافية جميعا، ونشوفكم على خير إن شاء الله.
يعطيك العافية دكتور أحمد.
Thank you very much
يعطيك العافية
again.
جميعا.
A nice evening for all.
يعطيكم العافية. شكرا لك دكتور أحمد. شكرا دكتور سلمان.
دكتور
شكرا لكم على هالمحاضرة. دكتور سلمان اشتقنا عليك.
تسلم. شكرا.
نحن إن شاء الله بنشوفك بإيطاليا، وبعدين هاي الدكتور أحمد السلايمة بتوجيهاته إن شاء الله بنشوفكم في اللاذقية بشهر 3 بحضور اجتماع لهاند.
إن شاء الله إن شاء الله بكل رحاب الصدر. سلم على كل على سوريا كلها. تحياتي.
يعطيكم العافية. أهلا جميعا. أهلا.
مع السلامة.
دكتور أحمد بعد شوي أحكي مع حضرتك.
إن شاء الله، يعني إن شاء الله 10 دقائق بكون في البيت. أنا والله جيت من الكرك، كان عندي مناقشة رسالة ماجستير وحتى ما وصلت، يعني 10 دقائق بكون إن شاء الله وصلت البيت.
ايه بدنا نحكي مشان موضوع بكره وشو تقررتوا مشان موضوع الأردن.
إن شاء الله إن شاء الله.
يعني
بنحكي دكتور على الخاص، بنحكي على الخاص إن شاء الله. مع السلامة.
أهلا.